Isaac Newton's Universal Law of Gravitation is one of the most fundamental principles in physics, describing the force that governs the motion of celestial bodies and objects on Earth. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This groundbreaking concept, formulated in Newton's Philosophiae Naturalis Principia Mathematica in 1687, laid the foundation for classical mechanics and revolutionized our understanding of planetary motion, tides, and the structure of the cosmos. Before Newton, scientists such as Aristotle and Galileo Galilei had different interpretations of motion and gravity. Aristotle believed that objects had a natural place in the universe and that heavier objects fell faster than lighter ones. However, Galileo's experiments with falling bodies and inclined planes demonstrated that all objects, regardless of mass, fall at the same rate in the absence of air resistance. Johannes Kepler's laws of planetary motion, derived from the astronomical observations of Tycho Brahe, described how planets move in elliptical orbits around the Sun. However, these laws did not explain why planets moved in this manner. Newton sought to provide a theoretical foundation for Kepler's empirical laws, leading to the formulation of his universal law of gravitation. Newton's breakthrough was realizing that the same force governing the motion of falling objects on Earth also governed the motion of celestial bodies. According to legend, he was inspired by observing an apple fall from a tree, leading him to question whether the same force that pulled the apple downward also extended to the moon and beyond. This insight led to the formulation of a mathematical relationship describing gravitational attraction. This equation signifies that the force of attraction between two objects increases with their mass and decreases with the square of the distance between them. The inverse square relationship means that if the distance between two objects is doubled, the gravitational force becomes 1/4 of its original value. The gravitational constant is a fundamental physical constant that quantifies the strength of gravitational attraction. It was first measured experimentally by Henry Cavendish in 1798 using a torsion balance experiment. The small value of g indicates that gravity is the weakest of the four fundamental forces, the others being the electromagnetic force, the strong nuclear force, and the weak nuclear force. Despite its weakness, gravity is the dominant force on large scales, governing the motion of planets, stars, and galaxies. Newton's law of gravitation provides a theoretical basis for Kepler's three laws of planetary motion. Kepler's first law states that planets move in elliptical orbits around the Sun, with the Sun at one of the foci. Newton's law explains that the gravitational force between the Sun and a planet results in an elliptical orbit. Kepler's second law states that a line drawn from a planet to the Sun sweeps out equal areas in equal time intervals. Newton's law demonstrates that this is a consequence of the conservation of angular momentum in a central force field. Kepler's third law states that the square of the orbital period of a planet is proportional to the cube of its average distance from the Sun. This can be derived from Newton's law by equating gravitational force with centripetal force. By deriving Kepler's laws from the Universal Law of Gravitation, Newton confirmed that gravity was the force governing planetary motion. Newton's law of gravitation has been confirmed through various experiments and observations. The Cavendish experiment in 1798, conducted by Henry Cavendish, measured the gravitational constant and confirmed that Newton's equation accurately describes the attraction between masses. Newton's law accurately predicted the motion of the Moon around Earth, validating the idea that gravity extends beyond Earth. The precise tracking of planetary orbits, including the motion of Jupiter's moons, confirmed the validity of Newton's gravitational law. In 1846, astronomers noticed irregularities in Uranus's orbit and used Newton's laws to predict the position of an unknown planet, leading to the discovery of Neptune. While Newton's law was mostly accurate, it could not fully explain the precession of Mercury's perihelion, which was later accounted for by Einstein's theory of general relativity. Newton's law has numerous practical applications, from everyday phenomena to complex astrophysical processes. The force of gravity determines the weight of an object and causes objects to accelerate towards the Earth. Engineers use Newton's law to calculate satellite orbits and design space missions. The gravitational pull of the Moon and the Sun creates tides in Earth's oceans. Space agencies use gravitational assist to change spacecraft velocity and trajectory using planetary gravity. Gravity plays a crucial role in the formation of celestial structures, from stars to galaxies. While Newton's law provides an excellent approximation for most cases, it has limitations. It does not account for relativistic effects near the speed of light or in strong gravitational fields. The precession of Mercury's orbit could not be fully explained by Newton's law. Einstein's general theory of relativity provided a more accurate description. Newton's theory does not incorporate the effect of gravity on time, which was later introduced by general relativity. Einstein's general relativity, formulated in 1915, describes gravity not as a force, but as the curvature of space-time caused by mass. This theory explains phenomena such as gravitational lensing, black holes, and gravitational waves, which cannot be accounted for by Newton's law. Newton's Universal Law of Gravitation remains one of the most significant achievements in physics. It provided a unifying explanation for celestial and terrestrial motion, revolutionizing our understanding of the universe. Despite its limitations, Newton's law is still widely used for calculations in engineering, astronomy, and space exploration. Einstein's general relativity expanded upon Newton's ideas, providing a more complete description of gravity, but Newton's law continues to be an essential tool in physics and astronomy. Newton's work not only reshaped the scientific world, but also laid the foundation for future discoveries, influencing generations of physicists and mathematicians. His law of gravitation remains a testament to the power of human reasoning in uncovering the fundamental laws of nature.